Greetings! I'm here to talk to you today about rate laws for chemical reactions. So, the rate of a chemical reaction is an indication of how quickly the concentrations of either reactants or products are changing. And we can either give the rate as a derivative if we want to be able to keep track at any instant in time how quickly the concentration of something is changing, or we can talk about it in more of an average sense over larger periods of time. But in any case, the rate of a reaction is going to be expressed in terms of the change in concentration of any of the reactants or any of the products over time. Now, just to have a concrete example to work with, let's say we have a reaction that involves reactants A and B and product C with stoichiometric coefficients small a, small b, and small c respectively. Now for this reaction, if we want to express the rate of reaction, we could express it in terms of reactant A, in which case we would have rate equals negative 1 over lowercase a dA over dt. And the reason for the minus sign is because when we think of a reaction, we generally think of reactants converting to products, in which case the reactant concentrations would generally decrease. And it's agreed upon that the rate should be defined as a positive value. So to get a positive, you need to have a minus sign in front for the reactants. And similarly for reactant B, we could express the rate of the reaction as negative 1 over lowercase b times dB dt. Or if we want to express the rate in terms of the product C and its change in concentration, we would write that the rate equals 1 over lowercase c dC dt. So negative sign is included for reactants, positive sign for products, because generally products are being formed or their concentrations are increasing during the reaction. So we can measure the rate in a lab as long as we have either a direct or indirect method of measuring concentrations. But then one important aspect of rate is that the rate is generally going to be related to some power of the reactant concentrations. And when we express the rate of a reaction in terms of powers of reactant concentrations, we have what's called a rate law. So for the reaction that we've been considering, A plus B yields C, the rate law would look something like rate equals K. K is called the rate constant, although it actually is not constant, but for a given temperature it's pretty constant. Rate constant K times the concentration A raised to some power M, and we don't know what M is a priori, times the concentration of B to some other power N. And one very important point about rate laws is that the exponents M and N, as well as the rate constant K, need to be determined experimentally. They're not quantities that you would be able to determine just by looking at the form of the chemical reaction. So there are many cases where the rate law looks like it could be deduced from the chemical reaction, but in general you have to be careful and say that you need to tie the rate law to experiment. It needs to be determined experimentally. So we're going to take a look at a sample data table where 3 experiments have been conducted, and in each experiment we have particular values of the concentrations of A and B that we begin with, and measured in molar, and the initial rate is given. Now, the initial rate is typically measured because if we wait too long, then the rate is going to vary, usually, and the longer we wait, the more the reverse reaction is going to convert product back into reactant. So that's going to interfere with what we're trying to study with just the forward reaction. So we typically measure the initial rate, measure the rate as soon as possible after the reaction begins. So in the data table shown, we have 3 experiments, and notice that between experiments 1 and 2, the concentration of B is held fixed. Usually we only vary one concentration at a time so that we can zero in on how that concentration affects the rate. So the standard procedure for determining the exponents m and n would be to compare different experiments with different concentrations. So if we compare experiment 1 and 2, then we should be able to figure out the exponent m, because between experiments 1 and 2 the concentration of A is changing while the concentration of B is not changing. So if we simply compute the ratio of rates between experiment 1 and experiment 2, as shown, what we see when we plug in all the values, because we know the initial concentrations of A and B in each case, we know the rates in each case, the constant K cancels out. What we see is that we can solve for m, and we obtain m equals 2. So the exponent for A in the rate law is 2. Now we can determine the exponent n by using experiments 1 and 3 or 2 and 3. Once we know m, it becomes a little easier to find n. So let's go ahead and compare experiments 1 and 3. So if we write the ratio of the rate of experiment 1 divided by the rate of experiment 3, again, plug in all of the numbers, what we find is that n equals 1. So m equals 2, n equals 1. Now we have the rate law. We know that the rate equals k times A squared times B to the first power. And so this is our rate law. The only thing left to be determined is the rate constant k. And to determine the rate constant k, because we know for each of these 3 experiments the rate and the concentrations of A and B, all we have to do is solve the rate law for k and plug in the rate, concentration of A, and concentration of B for any one of those experiments. And that should give us a value for the rate constant. Now notice that the units of the rate constant depend on how many powers of each reactant concentration are involved. Now another name for the exponent for each concentration is order. So for this particular reaction, what we determined is that this reaction is second order in A and first order in B. And you could also say third order overall. The overall order is the sum of the exponents of the reactant concentrations. So this is a second order rate law in A, a first order rate law in B, and we've determined the rate constant K, at least for the given temperature. It would be a different value at a different temperature, probably. So, hopefully that gives you enough information to be able to determine the rate law for a whole bunch of other reactions, if that's what you are tasked with. So thank you for watching, and goodbye.